So, welcome back to my YouTube channel. Today we want to talk about the Rademacher complexity, which is used to bound some properties in statistical machine learning. And for that, we need the risk and the empirical risk. So, our goal is to minimize the risk, which is the expectation of the loss, given that our variables x and y, so the inputs x and the outputs y, are random variables and have a joint distribution, which is in principle unknown. And we only have access to some data xi and yi. And for that reason, we can define the empirical risk. And our hope is that if we find an algorithm that minimizes the empirical risk, that we somehow also can bound the risk, which is defined by the expectation of the unknown random variables. So we're interested in the estimation error, which is the risk, so the expectation of the loss of our minimizer of the empirical risk minus the optimal risk, which is the risk of the minimizer of this this expression right here. So we want to bound the estimation error, and it is easy to see that we can bound this term by the supremum of the difference twice. And now we want to introduce the Rademacher complexity, which is just the expectation of the supremum of the average of Rademacher random variables times ti, where the vector t is just a vector out of this this set capital T. In other words, this term right here just tells us on average how good the set T can replicate signals of omega I. So omega I is just a Rademacher random variable, which means it's basically a Bernoulli random variable, but it takes values plus and minus 1 with probability 1/2. So it's like tossing a coin. And this this term right here just says how good capital T can fit this this random signal. So if we find for every random omega I a T such that the signs are always equal, then this term will be very, very large. And now we come to the theorem that we want to prove. Hence, we want to show that we can bound the expectation of this term. So this was just the term that was bounding the estimation error. It's important to say here that this this term here is a random variable, because the minimizer of the empirical risk depends on the data xi, yi that are assumed to be random variables. So we want to know what the expected estimation error will be, and this term we can bound by the Rademacher complexity, and this is what we will show right now. So we start off by this term, and then we rewrite the risk. The risk was just the expectation of the loss. So here we introduce the expectation of the loss of xi tilde, yi tilde, which have the same distribution as our other random variables, xi, yi, and these are independent, so it doesn't matter if we condition on the other random variables. In the next step, we can just pull the terms depending on xi, yi inside the conditional expectation, because when we look at this term, we have the first term was just independent of xi, yi, so this is just the same as the expectation of L of a xi tilde, yi tilde. And these are obviously measurable, so this is just the same as this term. What we do now is that we upper bound this term by the total expectation to see why this holds. We pull the supremum inside the conditional expectation, and the expectation of the supremum is greater less the supremum of the expectation. So that's why we can pull this expectation outside and upper bound it. And when we have the expectation of the conditional expectation, this is just the expectation, the total expectation. That's why we lose the conditional expectation in this step. And this is where the Rademacher random variables come in. So we have these random variables which are symmetric. So the xi tilde and the yi tilde have the same distribution as xi and yi. So multiplying with an omega I, which is a random Rademacher variable, doesn't change the random variable. So just it's basically just multiplying it with the random plus or minus variable, and since it's symmetric, that doesn't change its distribution. So that's the same. And now we already see that this has kind of the shape of a Rademacher complexity. And what we do now is just split terms and then distribute the supremum over the first term and over the second term, and then we see that we have two supremums, and the minus omega I is also a Rademacher random variable, so this is considered also just a omega I. So in total, here we have a Rademacher complexity, and here as well. So in the end, we end up with 2 times the expectation of the Rademacher complexity of this set, which is just the set of all loss functions evaluated at xi, yi to xn, yn.